All right, before we before we move on to the next section, I did want to answer this last question. I ran out of time in the last video. Caps at 15 minutes. We did this question about MP3 players. We showed that there was 15% of people that lost their hearing in 93, 19.5% have lost their hearing in 2005 in these samples. So does this give evidence that the true proportion is significantly higher in 2005 than 93? And we found that there was convincing evidence. Okay. Part B says, can we conclude the introduction of MP3s and iPods have caused more hearing loss? The answer to that would be no. We did not run an experiment. Meaning there was no assignment of treatments. So we can't prove causation. Basically, we can only say that there's a difference. Maybe there was something else that happened between those years. Maybe, car audio is louder, stereo equipment is louder, or kids are playing more video games or watching more. Who knows? It could be something else. Maybe there's something in the air. All right. Experiments versus sampling. So comparing two proportions really leads us to a natural application of this is to compare the outcome of treatments in an experimental setting. So our confidence intervals and significance tests can be used for randomized experiments just like they can be used for sampling. We just make the following modifications. In an experiment, we need random assignment of treatments to the subjects. We don't need random sampling because we're not random sampling, perhaps. We just need to have random assignment of treatments. So we got to change the wording of that first check. If we're not sampling from a population, we don't have the 10% condition. If you're not sampling, then you don't need to make sure your sample size is less than 10% of the population size. If we're not sampling from two populations, we do not have to check the independent samples condition. Okay. It shouldn't be trivial that we can use a two sample z-test for the difference in proportions in an experimental setting. It's a little more complex about why we're able to do that, but that's kind of BAPS, a little beyond AP Stat class. So you can do it. We just need to make these modifications. Okay. So here's another example already done for us. We're going to go through it really quickly, but it's an experiment instead of a sampling situation. I'll also just remind you that you should always kind of think about your scope of inference. Now, that's something we covered earlier in the year. If you're sampling, then you can generalize to a population. If you do good random sampling, then you can generalize to a population. If you're randomly assigning the treatments, then you can prove causation. If you do both, then you can generalize to the population and prove causation. If you don't do either, then you can't generalize to the population and you can't prove. So every study is going to be in one of those four outcomes. You should think about that whenever you're writing your conclusion statement. Cash for quitters. In an effort to reduce healthcare costs, General Motors sponsored a study to help employees stop smoking. In the study, half the subjects were randomly assigned to receive $750 to quit smoking for a year, while the other half were simply encouraged using traditional methods. Things like, it's bad for your health, bad for your family, probably, just like those types of motivations. None of the 878 volunteers knew there was a financial incentive when they signed up. At the end of 1 year, 15% of those in the financial rewards group had quit smoking, while only 5% in the traditional group had quit smoking. So it looks like the financial incentive was effective in stopping smoking. It looks like it tripled. Well, it did triple the percentage of people that stopped smoking, but this again is in the sample. It's a 10% difference. Is that significant or not? I don't know. We need to run a significance test. I'm going to guess that it is. Do these results provide convincing evidence that the financial incentive helps people quit smoking more than traditional methods? So PI is the proportion of all workers that would quit smoking with financial incentives. Notice I'm not talking about a population here. We did not sample anybody from this company. Okay, we took volunteers and then we randomly assigned them to the two treatment groups. So don't say the true population proportion. You can put the word true proportion, but don't say population. The true proportion of all workers that would quit smoking if they were in this study and they had the financial incentive. This versus the true proportion of all workers that would quit smoking without the financial incentive. What kind of workers? Workers at this company like the volunteers. I can't generalize because I didn't sample, but workers like the ones in the study. Hopefully you get what I'm saying here. The HO, PI minus PN is equal to 0 against the alternate. I'm wondering if the incentive is greater than the non-incentive. So I'm wondering if that difference is positive. The subjects were randomly assigned to the treatments. I just changed the wording slightly. But this is going to cost you a point if you don't word this carefully. If you say the samples were randomly selected, no, there wasn't even a sample at all. 10% condition, don't even do it. Large counts, run it like normal. We do not have to make this statement anymore, so let's not. And we don't say that the samples were independent. I think we should say that treatment groups are independent, but I've been told by expert teachers elsewhere that that's maybe not needed or wrong or whatever. Let's not get into it. Name the test. This is a two-sample z-test for the difference in proportions. Now you might say, well, why would I call this a two-sample z-test? Well, that is the procedure we're running. The question is, why does a two-sample test work with experiments? Well, it's complex, beyond AP Stat, but it works. So we're going to use it. We can call it that. You want me to put this in the calculator so you can see it again? I did it on the last example. I'm not going to. It becomes so trivial. You just plug it into the calculator and it spits out what you need. We're really kind of assessing you on all this other stuff. So the test statistic was 4.94. The p-value was really small, 0.000. I don't know what else. Since that p-value is much less than 0.05, we're going to reject the null, meaning we do have convincing evidence that the proportion of workers that would quit smoking with financial incentive, we have convincing evidence that write this down, is alternative greater than, write the other one down, than the proportion that would quit smoking without incentive. And then this is kind of a nice, I put it in parentheses, kind of made it look like it's optional, but you really should word it like this: for workers like the ones that volunteered for this study. Again, unfortunately, we can't generalize to the entire company or to everybody in the world because we didn't sample from the company. We didn't sample from the world. So it's just effective for the people like the volunteers in this study. So it seems like the financial incentive is effective. This is optional. But you get a smiley face if you put it down. All right? All right. This I'm really going to glaze over because this is BAPS and I didn't spend any time on it in class and I don't really want to here either. The calculator only performs two-sample z-tests for the difference of proportions if the null has the form, the difference is 0. If I go to that menu, statistics, stat tests, 2prop, the alternate only has P1 is greater than P2, P1 is not equal to P2. We can't hypothesize a difference other than 0 on the calculator. However, these can be done. They just can't be done with our calculator. So if you're wondering whether, like if somebody makes a claim that girls, why do I always say girls and guys, that, I'm trying to think of an example. I'm going to say use girls and guys and talk about who's smarter, sorry. We got to claim that girls on average score 2 points higher on the English portion of the ACT. Somebody makes that claim and you wanted to test it because you're like, oh, girls aren't smarter than guys. They should be the same. You could test that that's an example for means. talk about proportions, that the percentage of girls that score over a 30 on the ACT. I'm struggling here. I can't come up with an example. But if you want to hypothesize that the difference in proportions is equal to 3% versus the difference in these proportions is greater than 3%, you could do that. I guess I could say the percentage of girls that score over a 30 on the English portion of the ACT is 5% higher than the percentage of guys that score over 30 on the English portion of the ACT. Something like that. If someone makes a claim, we'd want to test something like this. Okay. Calculator can't do it, but we could still do it. We would just have to do the test statistic by hand and just do this all by hand. Special stat software will do that for you, but really, don't worry about it. You won't be tested on it. All right, this leads us to section 10.2. We'll start that in the next video.